Okay, so since it's just the two of us here, I'm going to be not doing any new material, just reviewing material we've already gone over, and then maybe working out a problem at the end, depending on time.
Okay.
So quantum mechanics is, well, looking at the wave nature of materials, at least so far, we haven't looked at using matrices yet. So it was based, well, it's based on everything we've done, the Schrodinger equation. Now remember the Schrodinger equation, technically the Schrodinger equation, and for whatever reason, I'll make it three-dimensional. I don't remember if it's got a plus or minus I on the right-hand side because we never write it this way. So we have our time-dependent Schrodinger equation. And this is simply based on an energy balance. Somehow, I think it's a minus on the right-hand side. I don't remember. And one of the first things we did was we said, well, if we can separate the time part from the spatial part, we can make our lives easier. And so we made a time-dependent Schrodinger equation, or a time-only part, and then a space-only part. And so we quickly went from that to this, where we have the Hamiltonian operator is the operator that gives you the kinetic energy and, of course, the potential energy. And so the left side is kinetic energy plus potential energy, and the right side is equal to total energy. That's what the Schrodinger equation is. And we take that Schrodinger equation and we solve it to find what our wave function is. So the wave equation, the Schrodinger equation, is our wave equation that we use to solve for the wave function. And that wave function, what information does the wave function carry in it?
The probability of where it is. Of course, you can get the energy states. Nothing else comes to the top of my head.
Well, the simple answer is everything. It carries all of the information, all hidden in that little equation. And how do you get the information out of that little equation? Operating on it, right. So now with that wave equation, what comes out of the Schrodinger equation is not in and of itself done. You have to apply some boundary conditions, which I forgot to write here. So we have our boundary conditions. And I have those on a subsequent slide, so that's why they weren't here, I guess. We have normalization. What you said, the wave function, if we take the mod square of it, that tells us the probability per unit length of finding a particle there. And so if we were to add up the probabilities over all space of having a particle in our region, if we have one particle, then the sum of the probabilities better be 1. So that's what normalization is. It has to be normalized, so the sum of probabilities over all space is 1. It's a fundamental rule. It's one we've talked about over and over. I'm just reviewing. Orthogonality. We get multiple solutions, and each one of those solutions has to be orthogonal to all of the rest. Orthogonal being a word that fundamentally is the same as perpendicular or normal. Perpendicular is two-dimensional, right? My fingers are perpendicular to each other. Normal is three-dimensional. My finger is normal to my palm. And orthogonal is infinite dimensionality. You can have any dimension you want. I should say undefined dimensionality. But each one has to be perpendicular, if you will, to the others. Perpendicular doesn't make sense if you have more than two dimensions. What does perpendicular or orthogonal mean in quantum physics? Orthogonal means that the integral of psi n star psi m dx is equal to 0 unless n is equal to m. Now, this equation would say it has to be 1 if n is equal to m. That's the normalization condition. So if you put these two ideas together, it gives you what we call orthonormal. The solutions have to be orthonormal, which means this one equation that will become a different color in a moment. This one equation combines both orthogonal and normal as one equation. Okay, probabilistic interpretation. Einstein did not believe that God played dice with the universe. He did plenty of work with quantum mechanics, so he was able to do it, but philosophically, he did not think that it meant what we think it means. It's kind of like that word inconceivable, if you're a fan of Princess Bride. Sorry, now my mind's going the wrong places. I'm wanting to quote lines from movies. Einstein pretty much figured we just don't understand enough about nature. Yeah, these probabilistic calculations give us the right answers, but if we knew how things really worked, we wouldn't need to rely on probabilities. If we had the right information, exact enough information, just like with chaos, if you have exact enough information, then you can describe what's going on in a chaotic situation. But you have to have the exact information. That's kind of how Einstein felt this must be. But as we understand things more today than we did when he died, it really is the fundamental nature of the universe, that there is a probability aspect to nature, that it's not deterministic, that you cannot say this, hence that for everything. And then we've talked about operators and observables. Observables are really the fundamental important thing in quantum mechanics. Quantum mechanics, you're trying to make predictions about what the observables will be doing. And so the observables are what you can measure. For anything to be science, you have to have predictions that can be tested. And so those predictions are going to be, what is the expected momentum? If I take 1,000 measurements of momentum, what's the expectation value, the average that I'm going to get from all those measurements? Quantum physics makes a prediction, and then we can test that against the actual experiment. Now, with that said, I at least have read and totally believe this to be true. Quantum physics is not really based on strong theoretical grounds. It's kind of nebulous in where it comes from in terms of theory. So we can't say that it's something that has a very firm foundation that really you should believe based on theory. You know, it makes it kind of pseudoscientific almost. But the reason we do it is because it has been shown over and over and over again to give correct predictions. So just like with anything else in science, you do enough experiments, test it enough ways, you start to have faith in it, even though we don't have a lot for the grounding of that faith other than it makes correct predictions.
Quick question.
Yeah.
Did we start the recording?
Yes, yes, we did. I am 100% positive, but I'm going to check just because we had, okay, you see that second one that says screencastify, blah, blah, blah. That says it's recording.
Yeah. Make sure I can watch it later, and Chris can watch it.
And then Chris can watch it, I know, because I felt so bad. He's not here for class. And, oh, sorry, no recording. No, that was him that wasn't able to watch, right? The other one?
Sorry?
Or was it him missing or you missing when I didn't get it recorded?
I think it was him.
Yeah, I think it was him. You missed more class. He's the one that got jobbed out of it. Okay, the problems we've tackled. We did a particle in a box. I believe that was our first problem. I didn't actually look through the book. I relied on my memory for this. But we did the particle in the box. Then we did the quantum harmonic oscillator, which seems like a long time ago now, even though it was, 2 weeks ago. We did the free particle. And with the free particle, we had a little hand waving because you can't normalize the solution for the free particle. but we could still do some work with it. Then we did the delta function potential wells, and finally the particle and the finite potential well. Did I miss anything that we did that you remember?
I don't think so, because the infinite well is basically the particle in a box, right?
Yes, particle in a box is an infinite well.
Yeah. I think those are all the main concepts. Yeah.
Okay, so there's a lot of things to learn in those, and even though our test will be technically only chapter 2, which is that, you obviously have to have some knowledge of the particle in the box for the particle in the finite potential well, right? Because it carries over. So the steps we used in every problem, for the most part, was we identified the potential energy function first. Without the potential energy function, we don't have anything to go on. Then we used the time independent. See, now my mind, we talked about, I mentioned a movie quote, now independent, like infamous. What does infamous mean? Oh, it's like more than famous, infamous. Yeah.
Really famous.
From the Three Amigos.
Oh,
the infamous El Guapo. He's not just famous, he's infamous. Anyway, moving on. So we use the time-independent Schrodinger equation to find a solution in each potential energy region. So for the particle in a box, we had 3 regions: outside the box, and in the box. For the simple harmonic oscillator, we only had 1 region, because the simple harmonic oscillator, technically, you have a potential well that goes on to plus and minus infinity. So we only had 1 region. Of course, in that solution, we had some interesting math we had to do. We had either the ladder operators, that was a new thing we learned with the harmonic oscillator, and then we also had the analytical method. Let's start by just finding a solution in the very large radius. And then we said, okay, so that's the large radius solution. Our total solution must be that times something that works in the medium to short range. And so we then put the two together and found our total solution. That was using some interesting math. And we will be doing one where we have 3 ranges: long range, short range, and then the intermediate. I think that's hydrogen atom, actually. So we use that time-independent Schrodinger equation to find a solution for each potential energy region. Then we applied our boundary conditions. And notice I put if they exist, because if the region goes on for infinity, then there is no boundary. And we normalized to solve for 3 things: quantization conditions. Without boundary conditions of some sort, the particle in a box still had the harmonic oscillator had a practical boundary, because if you go to infinity, it does have a potential approaching infinity. You have quantization. Without any kind of boundary, you don't have quantization. We found the constants, so psi is equal to A times this plus B times this. We found the constants, and we normalized the solutions. So my next to last slide, what are our boundary conditions? The first one is always, the wave function must be continuous. Always going to be a boundary condition. The second one has 2 pieces, except for the case of an infinite boundary, which is a made-up textbook problem. Then you have to have the derivative of the wave function with respect to space, i.e. the slope, is also continuous. If you have an infinite boundary, a textbook problem is the only one that has that, then you're going to have a discontinuity that you can actually determine, discontinuity in the slope, so going like that, whatever, that you can determine from integrating the Schrodinger equation. And I know you had sent me an email, made me feel, I was just talking to my division chair. She was asking how the class is going. And it's like, only once has a student contacted me outside of class with a question, which is disappointing. It's disappointing because I'm sure that you have questions. And when I'm not getting them, then I'm like, how are they learning? So, just just another encouragement. If you have questions, contact me. Don't say like, well, I wish I had the resource. Go ahead. Anyhow, so you asked me about that, and that's why I went through it last class period, to make sure you can see how we dealt with those discontinuities and how that actual integral of the Schrodinger equation worked out when it wasn't a boundary at x equals 0, which was the example you had before doing that problem. Do you understand now the answer to your question for what you emailed me?
Yeah, definitely.
Okay.
Yeah, it makes much more sense now.
Good. Okay. And then the final one here, not really a boundary condition, but a condition that must be met. In order to have a normalizable wave function, it has to approach 0 as you approach infinity. Anything short of that, and, well, we have a problem. Something new I just realized. I can see how long I've been lecturing by looking at the screen. Bottom left-hand corner says I've been lecturing for 18 minutes and 12 seconds. Well, okay, so let's look at a new problem now. Unless you have any other questions you want to ask before we go on to tackling a new problem. And this is a problem that I have not done yet, that I'm going to have you lead out and doing. So any questions you want to ask?
No.
Okay, so let's do this problem. Here's the potential function. How is this different than the finite well problem that we've just done?
It's going to break in the voltages at 0.
Well, not voltage, but potential energy.
Potential, yeah, sorry.
I obviously see why you said voltage, but so if we draw a first step in doing the actual solution, that's always useful is to make a picture. It's always useful because in the end, you're trying to solve for some situation and you want to not lose track of that situation. So I would definitely start by drawing a picture. Now, what is this picture? On this axis, we have potential energy. And on this axis, we have position. With the way I've defined things, that's x equals 0, x equals a, x equals minus a. And for the verticals, minus V2, minus V1, 0. So here we have a beautiful picture. Now let's go for solutions.
So I guess we start in one of the sections.
Okay, so let's name the regions. What would you like to name them?
1, 2, 3, and 4 from the left, I guess.
Okay, that works for me. I mean, you could have gone Adam, Bob, Carla, and Della for, that would have worked too, right?
Yeah. Okay.
There is one more thing we need to specify really before you get started. I did not specify this, and that is, what's the energy?
What do you mean by what's the energy? Like, is it positive or negative, or?
Well, there's really 4 different energy realms you could solve in as well. You could solve for energy less than V2, in which you get no answer. You could solve for energy between V1 and V2, which will give you one distinct set of answers. You can solve for energy between minus V1 and 0, which will give you a second set of distinct answers. Or you can solve for positive energy, will get you a third set of distinct answers. The reason you have different sets is, let's say this is case A, case B, and case C. In case A, you have a sinusoid only from 0 to A, and then you have an exponential decay in region 2 and an exponential decay in region 1. If you are up above in B, then you can have sinusoids going through regions 2 and 3. Not the same, but it'll be sinusoids. Yeah. And then if you go up to C, you'll have exponential, or you have free particle then. It's not, we saw the free particle will scatter off of the well if it's up there, so it's going to be different than just a free particle. But we're usually not very interested in that solution. So there's two that we might consider solving in. Choose one. I'm sure we'll not have time to even complete one, much less do both of them. But so which variation do you want to use, A or B?
Let's do B.
Okay. I'll call it region 1B.
So do we start by looking for a equation that fits the exponential decay in that region?
Right. Because we've done it so many times, you know what you have. But we start with the Schrodinger equation and find the solution. That's always going to be this step. And so we start with minus h bar squared over 2m d second. Now I just make it a straight d. I don't even make it a partial because x is my only variable. Dx squared psi 1 plus 0 psi 1. There I explicitly put in the value for my potential energy. Obviously, if it's 0, you don't need to write it down. Equals E psi 1. So we have that equation. We know the solution has the form. You tell me, what's the form of the solution?
E to the dx?
Yes. And so I know you're writing things down, but I wrote things down that I said I better erase that because I need you to tell me. I want you to go through the process to make sure you've got the steps.
So if psi is e to the bx, something along that line, those lines, then the second derivative with respect to x should be b squared psi 1.
Okay, what's next?
And so then I guess we could plug that into the Schrodinger equation. We could find E.
Well, what did I leave off in my little brace there?
Well, it would equal 0 if psi was equal to 0, but that doesn't make sense.
Right, that's the trivial solution that we don't use. Now, we didn't actually rearrange this to equal 0. It's just a true statement. To make it equal 0, we rearrange it too. There. So the two things that make that true, the first one was the trivial. What was the other one?
Where all that equals 0.
Okay, so that would solve for b is equal to plus or minus the square root of
2me over h squared. Yeah.
Why is there a minus sign inside there? Why didn't I put I?
Because your energy is negative.
Because my energy is negative, right? That's a really important thing to keep in mind when you're going through this.
Yeah.
And then it's just for convenience that we define kappa is equal to square root of minus 2me over h bar squared. We don't have to make that definition at all. It's just we would spend twice as much time writing out our equations. Okay, so all of this, I mean, you knew where this was leading because we've done it enough times. And so having that knowledge is good, but if it was like a test question, I would want you to show that you know where it comes from, what the steps are, not just, well, I learned it goes here.
Yeah. Okay.
Okay, so what do we have then for our solution?
So then we have e to the kappa x plus e to the negative kappa x. Or a, of course, with constants. A e to kappa x plus b e to the negative kappa x.
Right, because we had two different solutions for b, then we had to have a linear combination of the two. And then there's one last step.
Then we can make the assumption, since x goes from negative a to negative infinity, that the b has to be 0, because otherwise it would fly off to infinity.
Correct. So here's our solution in the first region. Which is sehr gut. I always mix my languages, you know, like sehr bueno. All right, so we found region 1B. Now what? That was one of 4 regions.
Okay, so let's find the next one.
Yeah.
Region 2, B.
Actually, let's make life easy. Region 4B. Why region 4B?
Because it's so similar to region 1B.
Exactly like region 1B, except negative exponential. Right, because this one, we have to have the positive exponential is the one that has the 0 coefficient. So it just will save us a lot of time to just go straight to okay, so we have A, B, C, D, E, F, G, H. I'm going to just use G. All right, 2 down, 2 to go. So how do we solve region 2B?
Start with the Schrodinger equation.
Excellent, excellent. So start with the Schrodinger equation. Whoops.
This one has a voltage of negative E1.
Once again, it's potential energy. It's
okay, so we do the same thing, I assume. So we assume that it has dx. The second derivative is b squared.
all right. And I'll rearrange this. And what do we have for solutions to that?
And so, of course, we have a trivial solution. And we've also got whatever b is equal to from all that, plus or minus square root of b negative e minus b1.
Okay, it's 2m e plus v1. Because v1 is a positive value, e is a negative value, but v1 is a bigger value than e. So there was a negative sign. If I would have solved this, I would have had b squared is equal to minus 2m parentheses e plus v1 over h bar squared. But because e plus v1 is a positive value, that means I'm taking the square root of a negative. And so the square root of the negative is why I have the I out front. And then I have this, so it's going to be a positive value inside the square root.
Right, yeah. So I've got that part of it.
So it's virtually the same, except for in this case, we had the square root of a negative, so we had to bring out the I. And we will define, let us say, I'm going to be dangerous and use K. So B is equal to plus or minus IK. Where from there?
So now we can write our equation as psi 2 is equal to cosine of kx plus sine kx.
Okay, we can do that. I like to use the C with cosine. I know the textbook used C with sine. I had to actually change my entire solution because after I'd done it, I saw the textbook use it oppositely.
Yeah.
Okay, that's one option. The other option is a different C. So I'll put C1 e to the ikx plus d1 e to the minus ikx. It can go, you can use either one. It depends on the problem, which one's more convenient. So that's why I wrote them both. Okay, now in this case, we had what was I going to say? I got stuck on changing the color. We had no going to plus or minus infinity. So because we're not going to plus or minus infinity, we don't have anything to say, oh, let's cut this out or something. So we're just done until we apply boundary conditions. So that's region 2B. Now what about region 3B?
So the only difference in this one will just be, it'll be V2 instead of V1, right?
Yes.
We really need difference.
So now I'll define L is equal to square root of 2m e plus v2 over h bar squared. And we have that for our solution. So we have now found, we found that I can't scroll well. That may not be a revelation though. We found our solution in each of the 4 regions. What next?
So at this point, I've forgotten what we're actually looking for.
Well, in a problem like this, you're looking for the energy levels and the wave functions.
So then, at this point, is when we're looking for energy level E. Since we have the wave functions.
We are angling to get there, yes. How do we get there?
So we apply boundary conditions.
That's right. We have to apply the boundary conditions. How many boundaries do we have? We have 3 boundaries, so we're going to have to apply the boundary conditions at each boundary. That's going to give us how many equations? 6. Yeah. It's going to give us 6 equations, and we are then going to have normalization condition, and with a whole lot of math that I'm sure we don't want to do, we would be able to solve for the energy levels and the constants. So let's see how far we can get. So I'm first going to just summarize by copying down our wave equations for each region so we have them all together. So we have uh-oh. Something is on a downward spiral. OneNote just crashed.
Oh.
Yeah, I guess maybe you couldn't tell I was sitting there trying to write and no dice. I was actually oh goodness. Kidding me? How long until it crashes again? I was well beyond this. Did you see my writing beyond this, or did it disappear?
I saw it, yeah. Yeah, I saw it. You wrote this entire one and started the 3rd one.
Yeah. I was right here when it crapped out, or no, right here, trying to write the E. Oops. All righty. There's our solution. Now boundaries. BC for boundary conditions. One to 2. What are my 2 conditions I'm going to have?
Okay, so they have to be continuous.
Mm-hmm.
And in this case, the derivative also needs to be.
Right. So let's just apply the first one.
Okay, so the first one, so that would mean that psi 1 of negative A has to be equal to psi 2 of negative A.
using the rules of even odd rules for cosine and sine. I'm converting it into positive angles. Okay, so there's that boundary condition. What's the next boundary condition? You said it.
Okay, yeah, the next one was the derivatives have to be continuous. So, yeah, so D1 at negative A in D2, yeah, so
and notice I'm not saying the derivative of psi is a function of A, because of course that's incorrect. It's evaluated at minus A. And so doing the derivative of psi 1, that's going to just bring down a positive kappa. And derivative of cosine kx is minus k sine of kx. Derivative of cosine is positive sine, or positive cosine. Derivative of sine is positive cosine. Yeah. And once again, using the rules to make it so the angles are positive. So there's my two boundary conditions at the first region. Next region.
so, 2, 3. So it'll be the same thing technically, just at a different place. So side 2 at 0 has to be equal to side 3 at 0.
So that's going to be C cosine of 0 plus D sine of 0 equals E cosine of 0 plus F sine of 0.
It's so nice when things are at 0.
Yes, it really is, because the two sine terms are 0, and the cosine terms are 1. So what I have is C equals E. That boundary condition was really, really simple. Okay, next one.
The next one is just the derivatives at 0 have to be equal.
So taking those derivatives, that's going to be LE and once again, sine of 0 is 0, cosine of 0 is 1, and I get KD is equal to LF. So I've got some pretty simple relationships between these two. Like you said, it's so nice when your angle is 0.
Yeah.
All right, final one.
The last one is at A.
Whoops, did that backward. And I put K's instead of L's. Right? And finally, you notice after the crash, I think my pin has become fatter.
Yeah, I did actually.
Ah, goodness gracious. There's my last equation. Now, with all of these equations, we only have a minute left in class, so we're pretty much done with what we can do here. We would now need to start combining things. Yeah, definitely got fatter. Well, actually, it wasn't at the crash because the crash was in this region, and it got fatter right here. Kind of confused, but we now have these 6 equations. 2 of them already were simple and reduced one variable in each one. So we really only have 4 unknowns instantly out of the 6, 2, 4, yeah, out of the 6. And then we combine the rest of the equations, and we will find our quantization rule without having to use normalization. Then we use the normalization, and we would be done. And yeah, if you feel that you have that kind of time, you can. Oh, that fit perfectly. Okay, so I'm not going to put a box around that one. You can combine these 4 equations and actually find your solution. Why don't we do this one as a general part of the class? Well, because once you've gotten to this part, it then just becomes a hassle. It's not like you can't solve a set of equations. It's like a real hassle to solve the set of equations. All right.
But we still have to solve for E, though, in the L and the
Yes,
A
that's right. The L, K, and kappa, all 3 of those are really just functions of E. And so we have 6 constants, A, C, D, E, F, and G, plus a 7th in the E that is hidden in those 3. So we have 7 unknowns. We had 6 equations here, plus normalization gives us the 7th. We have enough to solve for everything. And it'll give us the quantization plus, the normalization with the last one. So that's where we'll leave it off. I'll see you a week from Monday, right?
Yeah, that's right.
Have a great spring break. Hope you have a lot of fun.
I will. And so the test is on that Monday we come back, right? Or is it on?
I was planning on the Monday. That's why I mentioned on, this past Monday. And my understanding was that you and Chris said that was fine with you, right? Yeah, if you have an objection, let me know because I'm not trying to force it.
Yeah, no, that's good.
Okay. All right. So I'll see you in a week and a half.